Recently, I've been learning to write compute shaders. For my first compute shader project, I tasked myself with creating a battle simulator which can simulate millions of units in real time at a stable frame rate. In this video, I'll be using compute shaders in a much more practical way, in creating procedural destruction and reconstruction effects with compute shaders. I'll be using the Bevy game engine for this project, not because of any particular benefit that it provides for this specific project, but because it's the engine I'm the most familiar with at this point in time. I'm going to start by giving a brief overview of what compute shaders actually are, because a lot of you are probably not too familiar with the topic. Compute shaders are a way for us to perform more general purpose calculations with the GPU, which are usually done on the CPU. Right, so how do we actually use compute shaders? I explained this a bit in my last video on compute shaders, but I'm going to explain it again because I feel like the explanations could have been a lot better in that video. The first concept we need to understand are workgroups. Workgroups are basically a block containing worker threads. The worker threads are the ones actually performing calculations by executing a certain function in parallel. Compute shaders function by dispatching multiple workgroups and arranging them in a block just like worker threads are arranged in a block within workgroups. Each worker thread has a global invocation ID, which is just the position of the worker thread within the entire compute shader pass, or to be more blunt, its position within the block of workgroups. This ID is usually used to perform parallel processing of images or arrays, which are very easy to process if you arrange workgroups one-dimensionally for arrays or two-dimensionally for textures. Then each invocation ID corresponds with either an index in an array or the position of a pixel in a texture. Okay, with that out of the way, let's actually get into the implementation. I first started out by creating some assets for the game, because it would be rather boring to just destroy white squares. It turns out that years of half-assing my way through creating art assets for my little hobbyist games actually produced some results, because I think these animations look pretty decent. The walk cycle looks a bit unnatural, but it can't be helped since I'm not very competent at art in the first place. I also created this basic tile set and background image. Then, using the Tilemap editor, I made this simple scene, and after recycling some code from one of my previous videos, we now have a basic 2D platformer scene set up. Let's get straight down to business. First, we need to find a way to render a sprite using compute shaders. More specifically, I want to be able to represent every non-transparent pixel in our texture as a particle that we can manipulate and apply physics to. Let's start out with a basic particle structure with a position, velocity, and a rotation field. I'll also add this integer parameter live, which indicates whether we still need to update or render the particle. Once an object spawns into our world, we will iterate through all the pixels in the image and calculate the world position of each particle in the image while adding it all to an array. After creating a particle buffer from this array of particles, we want to pass this information onto the GPU. To accomplish this, we can then create a bind group for our rendering operations consisting of our particle buffer, the screen texture that we're rendering to, a uniform variable buffer which contains some important information that we're passing from the CPU each frame, and finally, the image texture of the sprite that we are going to be sampling from. Then, when it finally comes time to dispatch our rendering pass, we can iterate through all of the entities with a destructible component attached to them. Then we can find the associated rendering bind group with the entity, and given that each of our workgroups has a one-dimensional size of 8, we can calculate how many workgroups need to be dispatched per entity by just dividing the total amount of pixels in the image by 8. Now let's take a peek inside the actual rendering shader. We have a clear function which is dispatched before all the rendering operations every pass, ensuring that the texture is blank before we draw to it again next frame. Then in our render function, the world position of each particle is first converted to screen space in a relatively unconventional way. I think there is definitely an easier way to do this, probably with matrices or the like, but this works for now, so it's what I'm going to be sticking with. There's a bit of jittering, but the goal of this video is to create destruction effects, not to fuss over every detail like I'm actually releasing a game. We then find out what the color of the current pixel should be by sampling from the texture of our object using the order in which we put the particles into the buffer array as a reference. Finally, we will be rendering to the actual texture, only if the pixel which we just sampled isn't transparent. If the particle is transparent, we flag the particle as dead by setting its live parameter to 0 and don't render it. Otherwise, we can just set a pixel on our rendered texture to our queried color. There's a little bit of jittering when the camera moves and when the player is in a certain position, but we'll worry about that when it actually matters. Our next goal is to actually have all of these static particles that we just rendered be able to move around and act according to the rules of physics. A basic destruction effect like the one on screen right now is our end goal for this chapter of the video. In order to do so, we need to first communicate to the GPU when our player initiates the destruction of a rock, which is first done on the CPU side, where we set a trigger flag to 1 when the player punches a rock and communicate where the player punched so that we can use this information later on the GPU. Then, when we go to dispatch our compute shader functions, we can check to see if the flag has been triggered and whether the rock has already undergone destruction. If the rock has not yet undergone destruction and our flag has been triggered, we can dispatch workgroups to run a compute shader function that triggers the destruction of the rock. Also during this time, time, we can run an update function for all of our particles, which will update the logic and position of the particles within an object. Let's take a look at these shader functions now. First off, the trigger function finds the direction a particle should take to move directly away from the point of impact of our punch. This direction variable is then used to set the velocity of our particle based on a certain ratio between the x and y axes for more customizability. Then, to add some variation, we find a random angle and convert this to a direction using trigonometry. This is then used to add a little random offset to our velocity in order to make the effect look more realistic. Then, within our update function, we first check to see if our particle is alive. In our current state, the only requirement for being alive is for our particle to not correspond to a transparent pixel on the input image for our object, because this would mean the particle should never have been instantiated in the first place. If the particle is alive, we first apply a gravitational acceleration to our particle, only if the velocity of our particle is not zero, because the velocity of our particle should stay zero until the trigger function is called for destruction. The position of the particle is then updated based on the velocity of the particle and a delta time, or the time between the current frame and the one before it, which is passed in through a uniform variable. I could also have made this simulation run on a fixed time step, but accuracy isn't really one of my goals here. And with that, we have the basic destruction effect finished. We can now go around punching various objects and watch them satisfyingly deteriorate. Tweaking some parameters also allows for some spectacular but unrealistic effects. Speaking of realism, you might notice very little in the behavior of these particles. And no, I'm not talking about them moving at an unrealistically quick speed after being punched, or the fact that a regular human is even able to punch through rocks. The particles from destruction have no concept of collision. They ignore the ground and just sink into the water after being destroyed. Let's change that. I think that programming game physics is one of the most fulfilling features to work on as a game developer, but I'm going to be less ambitious than I usually am when implementing physics and just have the particles interact with the collision tile map. The first thing we need to do is actually pass in our collision map to the GPU. Currently, our collision map is stored as a one-dimensional vector of enums. However, enums don't really work on the GPU, so we need to write some code to convert that array into an array of integers, where I will have 1 represent solid tiles and 0 represent empty tiles. A simple match statement accomplishes this task well. Now, just like we did with our particle array, we can convert this array into a buffer and pass it in with our bind group as a storage buffer, which we can then access within the compute shader. Let's go inside the shader once more and take a look at how we actually use this information. Our tile collision map is stored as a read-only storage buffer because we don't really have a need to modify the map inside of our shader. We can find the tile that our particle is in with some integer rounding operations. It helps that our particles aren't really bigger than 1 pixel in this prototype, because otherwise this collision operation would look a lot more complicated and be a lot more performance insensitive than it looks right now. Right now, we simply find which tile our particle is in and repel the particle with a certain restitution constant if we find that the tile is solid. Now our particles will actually interact with the terrain of the game instead of just passing through everything in existence. This makes the effect seem a lot more realistic, even if the physics aren't entirely accurate, as the particles don't collide with each other. Still, this already makes for some pretty satisfying destruction effects if we just replace our rock with some other objects. Breaking apart huge objects like this spherical ball or a giant tree really shows the power of compute shaders and the procedural destruction effect which we just made, because the process of manually creating different portions of a giant sphere to break down would take many hours of work and would still not be as realistic as using this procedural destruction effect. But something is still bugging me. This effect still seems a bit unrealistic, and this is because every pixel just scatters apart uniformly, which is definitely not how an object fractures in real life. It might look fine for smaller objects like this tombstone, but the unrealistic destruction still kind of bugs me. To remedy this, we need to make our object break apart in chunks. I don't mean this literally though. Each chunk won't be a single particle, but will be made up of particles which are pixel sized. This is perhaps a little difficult to visualize, so let me just show what the end product is like before showing the implementation of such an effect. There appear to be chunks breaking apart from the tree because every particle that should be part of a chunk has received the same random offset of velocity by hashing with Voronoi noise. Voronoi noise in its pure form looks like this, and it is generated by first creating a list of random points. Then the current pixel, or particle in our case, will check which point it is the closest to in the list and use that point as a random seed for whatever operation we're trying to perform. To generate this noise with compute shaders, we need to first make an empty array of points on the CPU, which you can then pass to the GPU as a storage buffer to populate. This is of course done by creating another entry in our bind groups and passing in our Voronoi buffer to them. Then, when it comes time to dispatch our computator passes, we can actually make use of this buffer. When destruction is triggered, we will run a function to generate all the random points in our Voronoi buffer before running our trigger function. The amount of workgroups that we dispatch this time is decided based on the amount of points that we wish to generate divided by 8, where 8 is the workgroup size. Hopefully some of you who are new to computators are starting to see the computator design paradigm now. Okay, let's again take a look inside of our actual shader. The Voronoi gen function is very simple. It merely generates a random point inside of our sprite's bounding box and sets the corresponding value in our Voronoi buffer to that point. This is all a setup for when we actually utilize the Voronoi noise by understanding and applying the algorithm within the trigger function. Inside the trigger function, we are finally able to make use of these random values. We first find the index of the closest Voronoi point to our current particle's position within our input texture. We can then feed this index value in as a seed for a random function, which will offset our velocity by a certain value, enough so that a relatively cohesive chunk appears when we punch an object. I think this is a very nice middle ground between complete uniform destruction and just making particles into a single chunk, which kind of ruins the point of using a performance intensive tool like a computator for procedural destruction. Even more so because we are simulating in 2D, so we don't really need complicated physics like 3D does. And with that, I think we've succeeded in making our destruction effect a lot more impactful and realistic. This is pretty much a completed destruction effect at this point, but we can create another type of effect with our current system with very little work, and that is the opposite of destruction, reconstruction. If you think about it, all we have to do for a reconstruction effect is make the particles move back towards their original position. So let's quickly go over how a simple reconstruction effect is done without taking up too much time, because I want this video to be at least done by the 15-minute mark. First, let's take a look again at our particle structure. You can see that it has changed a lot from the start of the video. We aren't actually using the rotation parameter, and there are probably more efficient ways to structure this particle, but this is still a prototype project, as is the case with most projects I make, so I usually let stuff like this slide. Anyway, the important parameters to take note of for reconstruction are this original position parameter and a reform flag, which is basically our cue to execute the reconstruction effect. It should be noted that we can also just calculate the original position parameter based off of the index of the particle and the position of the center of the object, which is passed in through a uniform variable anyway, but this is what I would refer to as over-engineering, so I just decided to add an original position parameter instead. In order to know when we want to reconstruct our objects, we detect when the R key is being pressed on the CPU side and set the reform flag to 1 on all objects with the decomposition component. Then, when it comes to dispatch our workgroups and run our compute shaders, we can use this flag to run a reform trigger, which is basically the opposite of the destruction trigger, where we reset the state of all objects and set the reform flag on our particles to true so that they will start returning to their original positions. Again, let's go inside our shader and take a look at this function that is magically able to reset our particles. This function sets the velocity of all particles to 0, activates their reform flag, and also makes it so that they have a new lifetime, so they can actually be updated in the update loop after being destroyed again by the player. Of course, the lifetime doesn't start ticking until after a destruction event is triggered. We don't really need to add any additional time onto the lifetime of each particle. Of course, it isn't just one function. We also need to make changes to our update loop so that it behaves differently when our particles have their reform flag set to true. Now this part might actually be a bit over elaborate, but I wanted to really make sure our particles could return to their original positions while staying true to our current physics system. I didn't want to make use of functions like lerp and slurp and directly modify our position component. We start off by setting the velocity of each particle so that it points directly towards its return position, and also through some clever mathematics, change the magnitude of the velocity so that they start off moving slow and get faster as they start to move towards their original position. Then there are two conditions that can be satisfied for having returned to their original position. Either the magnitude of velocity is greater than the distance between the position of a particle and its original position, or a particle is very close to its original position already. In both cases, we reset the particle's velocity and all of its states so that it isn't trying to move back to its original position anymore. The first iteration of our reconstruction effect is officially complete, and if you're still here, we've reached the end of the video. I'd really appreciate it if you would consider liking the video and subscribing to the channel, as it really motivates me to make new content and keep continuing on my game development journey. I hope you found this video at least a little bit interesting and that it helped you out a bit.